Hi, welcome to Why Measurements Matter, an introduction to measurement risk. This is kind of we've talked about this topic before, but this one add a little bit of new things, and I think at this time it's a very valid topic with everything going on in the world. So glad you could be here to watch this. And as always, if you have any questions or concerns afterwards, please note my contact information, hzumbrun@mhforce.com, or you can contact sales directly at info@mhforce as well. Risk management. Laboratory must plan and implement actions to address risk and opportunities. The laboratory is responsible for deciding which risk and opportunities need to be addressed. Now, we were just audited by A2LA, our renewal to the 2017 standard, and it was interesting because the point where we get to risk management and risk opportunities, we do these in a quarterly management review meeting where we discuss various opportunities. Of course, we have event forms, we're seeking feedback, we're doing everything we need to do, but the real direction is on the management meetings to review the events. You always want to strive to become better and look for the opportunities and maybe risks that you had identified and see if you were right or wrong. So once we do that, we're typically scoring it. We're saying risk equals the probability times impact. So you can look at it severity times impact as well, but in most likelihood, it's going to be the probability, and the impact is going to include the severity with it. So something like damage during shipping, probability is going to be high. Impact's also going to be high because if people don't get their stuff or if something's broken, then they lose all the history and traceability. So we have a policy to take pictures on everything before it goes out the door and as we receive it. If it comes in and we don't like the way it's packed, we'll repack it and send it out better than what we received it. So these are things that you can look at your flow chart and say, hey, I'm having a lot of shipping claims. I can only control what we ship out of here, but I can double box it. I can do things that'll be better for the customers. And when we look at risk management, we say, 2005 versus 17. 2005 had risk in it. There's policies, procedures, job descriptions, top management, quality manager. And whereas 2017, we're looking at documented info, processes, and decision rules. And a lot of 2017 focused more on minimalizing a lab's risk exposure, and many of the should references are replaced with shall, such is the case with some of these statements here. 7861, when a statement of conformity to a specification or standard for test calibration is provided, the laboratory shall document the decision rule employed, taking into account the level of risk such as false accept, false reject, and statistical assumptions associated with the decision rule. Now, there is a new version of ILAC G8. Highly recommend everybody read that. Breaks things down very, very well. The previous version recommended really using method 5. The new version gives you a whole tree. It is something that people need to ask. And then 7862 again talks about the decision rule applied unless it is requested specifically or in the standard. So if somebody says, hey, I want you to calibrate in accordance with E74, we just follow the standard. If somebody says, I want you to calibrate this device with a tolerance to 0.5%, we start asking about decision rules, ask questions. If you can do simple acceptance, you can do method 5, method 6. There are some rules that you can't do because you just don't have enough information. And when we start talking about risk specifically, what are we talking about? We're talking about a measurement decision risk as a probability that an incorrect decision will result from a measurement. Here's a nice graph. This is one standard deviation here on the graph, and anything to the left of the red line or to the right of the red line is risk. So ISO 17025 defines a decision rule as a rule that describes how measurement uncertainty is accounted for when stating conformity. Yeah. That's essentially what we're doing here. We're looking at this graph and we're saying, here's a tolerance band. How am I going to take into account measurement uncertainty? When I take into account measurement uncertainty, I want anything hanging over this graph typically to be less than 2%. In this scenario, that's 31.74% risk. That is way too much risk on anything. That means I have a 31.74% chance of me calling this measurement good when it's actually bad. So 31.74% chance of it being bad, and me saying it's good. So not too good on here. Here's just a simple thing. You can see you look at the PFA, that's probability of false accept. You look at your expanded uncertainty, and this one simply you subtract the measurement uncertainty from the value, and that's one of our certificates. A lot of people look at test uncertainty ratio. That's the ratio of span of tolerance of the measurement quantity subject to calibration to twice the 95% expanded uncertainty of the measurement process used for the calibration. This is found from ANSI Z540. It's a UUT tolerance divided by the calibration process uncertainty. We've seen it listed out this way. Different specifications, tolerance by the expanded uncertainty. We've also seen the upper specification divided by the lower, 4 times U. I don't like 4 times U because you don't know what you're working with as far as probability and confidence interval. So it's usually K, and it's usually 2 times the expanded uncertainty. If you want 95% confident, it can be 196. It just depends on how things work out in the equation. But this comes specifically, this denominator here on calibration process uncertainty comes specifically from 2 documents. ILAC P14 makes reference to the resolution. I know the test value uncertainty people hate this, but it is something that is in ILAC P14, as well as ANSI Z540 Handbook 3 talks about a lot in reference about the denominator and these are really what it says the minimum things to consider in a denominator, which are your CMC uncertainty parameter, divide that by whatever coverage factor you used. Resolution, here I'm taking the square root of 12 because I'm assuming it's digital. We have more courses on uncertainty. If people want to know how to calculate resolution, it's either going to be the square root of 12 or the square root of 3, and then the repeatability. If you did the repeatability for your CMC, you can take that out and put the repeatability of the device. Now there is a big debate on this with the test value uncertainty group, and it's just a matter of who's going to absorb the risk. Is it going to be the end user? If we don't do this in our lab, if we just give you the measurements and say go figure out your uncertainty, it's just going to push it to the end user. If you're making a measurement, they're going to have to figure out, oh, my band, I have a 10,000 pound device. I need to be in a 1%. Plus or minus 10 pounds, 0.1% plus or minus 10 pounds or something like that on the device, and then they're going to have to say, oh, instead of 0.1, I really need to be within 0.007 because I want to account for the measurement uncertainty. This is something on how that looks. So I have a 10,000 pound load cell 005 with a accuracy of 0.05% of full scale with a 0.01 pound resolution. If I run these through the formulas, 2 things are going to change here. One, basically the repeatability in a machine that's not as plumb level square and rigid as the other machine, maybe the alignment's not as good, of my unit under test is going to change, as well as my uncertainty, my CMC uncertainty parameter. Here we're using a dead weight machine, 20 parts per million, and we're comparing it with a secondary standard used by many of the labs down in the pyramid, as many of our competitors use, of 0.05%. Big difference, you have a TR of 22 to 1 versus 1 to 1. So when you start looking at risk and uncertainty and you start looking at how to lower them, one of the main things you want to do is use the right calibration provider and have them replicate how the device is being used, have competent technicians, use the right equipment that includes adapters. There's a paper we wrote on adapters, very, very critical. One adapter, you could tell us you want a 0.05% accuracy, and if you're changing adapters, you could have an additional error of 0.3%. So that 0.05% means nothing if you're changing adapters and have a 0.3% error on those adapters. So, and then you can lower your uncertainties through using a calibration provider with lower uncertainties. That's really tolerance required. This table here is saying how much risk, the tolerance required, where do you need to go. Anything in red would have too much measurement risk. So it really shows that, if you want a tighter tolerance, a tolerance of better than 0.02%, you really need to use dead weights. Even if you want a tolerance of better than 0.05, you really need to use, almost in all cases, need to use dead weights. Some you can eke in with some secondary standards there, but if you have devices or equipment where you want things to be, and your uncertainties, again, this is cumulative, so they're going to get larger. If we look at this graphically, we can look at, 10,000 pounds. Here it is graphically. One, you see the repeatability and you see the CMCs, you see a very, very steep curve. And the other one, you see a less steep curve. And all this is really is we're changing the uncertainties of the lab, where this was sent for calibration. Both labs have the same measured value. If we move it, you know, in this case, if we change the measured value to, 10,004, one lab can still say it's in and one cannot. So if you're looking to have a labs, make that statement of, conformance or compliance, depending on, they change that terminology as well. Depending on it, you want your device to be in tolerance. A lot of labs, when they account for that decision rule or take measurement risk into account, are not going to be able to give you the pass. If you're looking at a device that's 0.1%, and their CMCs are at 0.5, they're gonna have less of a window. And here's really, we're getting into it more about the standard and what's going on. The people that wrote the standard use 95.45%. So that's 2, has a coverage factor of 2. You can see that this slide, the risk is 2.275% or less when we enter 9. So really what this whole slide is guard bands to assume less than the risk. So this says I have a device, it's plus or minus 10 pounds. What happens when I actually apply my guard band and look at it here? So this whole chart is basically saying if I make a measurement on this device and my device, even though it's plus or minus 10 pounds, my device has to be, to assume less than 2% risk, this is in the bottom right corner, has to be 996.029 to 1,003. This was a 1,000 pound device that we were looking at, not a 10,000, but yeah, so down here is what we're looking at. 1,000 pound device. I need, if I want less than 2% risk, I don't have plus or minus 10 pounds. I have plus or minus 3.971 for 2%. And really, it just shows that a small relative expanded uncertainty, the acceptance interval is going to be a lot larger. So right here, if we look at this is Morehouse, dead weight, any lab really with dead weight primary standards, Morehouse, dead weight, or dead weight, any lab with dead weight is gonna have more than likely, smaller CMC uncertainty parameter as far as force goes. So you're going to have much more acceptance interval. And then here, down here, you're going to have your secondary, you're going to have your transfer or secondary standards. So going to be a lot smaller. And I kind of equate this to parking lot. If you look at a parking lot, the lab with the smaller uncertainties will produce larger TURs, giving you more space to be in tolerance. I like the parking lot scenario because you come in here, you look at this, and when you're looking at it, you're like, I can swing open that car door. I could probably put a lawn chair out here, sit people. I might even have enough room to social distance, maybe not. But I can do everything I want to do, and I don't have to worry about dinging the car beside me, as opposed to, I have this much room to be in tolerance. I'm using that lab with the dead weight machine. I can be fairly confident that they're going to give me the best probability that when I receive my device back, I'm going to have that statement of compliance, and I'm not going to have to worry about recals and some of the other stuff that goes along with it. You compare that to a lab with the larger uncertainties, will produce smaller TURs, giving you less space to be in tolerance. Here in this case, when I open this door, I'm going to have to suck in everything. I'm not as svelte as I once was, but I'm going to have to suck in everything and shimmy, and I'm going to have to be very careful. I can't just throw open this door. I'm going to dent the car beside me. So really, again, the smaller uncertainties give you a lot of room to be in and a lot more room to make that statement of compliance. So questions for people, generally, have you or any of your technicians ever overloaded a load cell? This happens frequently. It's not horrible. It should be a learning lesson. There are some things that you can do. If you're at constant risk for overloading load cells, you can buy load cells with higher capacities. like for example, if you wanted a 2,000-pound load cell, but you thought your techs were going to overload it, you might consider using a 5,000-pound load cell and just derating it to 2,000 pounds. Overload or permanent shift would happen at 7,500 pounds in that scenario as opposed to 3,000. Have you or someone you know ever used the wrong equipment to try to accomplish a certain task? That would be, hey, we need to get this done. Just use what we have. How about signing a certificate you were unsure about? Do you know of any bad measurement practices in your organization that are not being corrected, or do complaints fall on deaf ears? Do you have adapters, like unsafe adapters that you'd like to replace, but management doesn't want to? They should be replaced. How about your calibration provider? Have they just ever admitted to making a mistake? If the problem was not corrected, did it just go away? No, calibration providers typically they're not going to admit. I know several that have. We've been on the course where we've had to do recalls. They're very, very painful, especially when you found it. Fortunately, the one that I remember the best, we found it within a week, so we only had a week of data that we had to worry about. But it's still painful. And what we found is it was in relation to Agilent Agilent 3458A. We found numbers were entered wrong for a week, so we mathematically could go back and correct everything because we had records of what we did, but still not great. We're not perfect, but we can mitigate measurement risk by making better measurements and by replicating the proper use of all instruments to lessen the possibility of devastating errors. So we're really talking about, we're talking about risk and why measurements matter. Well, here's a neat example. It's the Swedish warship Vasa, which famously sank in 1928, less than a mile into its maiden voyage. It was built symmetrically. And when they go back and they look at this stuff, they found out that the rulers used by the workers, two turned out to be based on the Swedish feet with 12 inches, 30.48 centimeters, and the other two used Amsterdam feet with 11 inches, 27.94 centimeters. So if you're measuring something and want to make it look larger, you use an Amsterdam foot. And no, in seriousness, this happens all over, everywhere, and there's lots of examples of people using it. In fact, recently, a mission to Mars, the rover, there's one group was using SI measurements, and the other ones were using customary, English customary, and things were not right. Same thing with a couple of moon landings recently that they anticipate that the wrong calculations were made. So why measurements matter? Those that do not know what this is a collapsed bridge. This is one that was happened during a NCSLI convention out in Minnesota. The likely cause of the collapse, noting that too thin gusset plate ripped along the line of rivets and additional weight on the bridge at the time contributed to the catastrophic failure. And the question is, was the gusset plate ever tested? So they find out after things happen that maybe we had too thin gusset plates. Were these contracted? There's lots of things we do not know about it. Where was the testing? Where's the cert? All we know is countless people died, and they really did not need to die. Another one here. Here's this span that was just, to me, silliness. This is northmost, said the NTSB said errors were made in the design of the northmost nodal region of the span where two truss members were connected to the bridge deck, and those errors resulted in an overestimation of the capacity and an underestimation of the load placed on the section. This killed 6 people. All it takes is, the main thing is you can do simulations, and simulations without testing is basically garbage, because all it takes is someone entering a minus instead of a plus in software that does the analysis. It's just an example of why testing is so critical for everything that happens. Here's a video. That's a stealth bomber. This is going for takeoff. What happens here? Something's not right. Pilot ejects. Right there, the pilot ejects. And now you crashed a plane. And why did we crash one of our most expensive bombers? Well, let's see why that happened. There were two intertwined causes of the crash. Heavy rains before takeoff caused the fuel to get into the data sensors, which were responsible for calculating speed and altitude, amongst other things. And the mixture of water and fuel caused condensation to build up on the sensors, which were near the plane's surface. When maintenance crew were calibrating them before the flight, they were unaware of this buildup, causing them to calibrate them wrong. Kind of like fixtures, unaware. You don't know what the fixtures are doing to your cow or to the output, especially of load cells, very mechanical. And this one was only a $2 billion mistake. So starting to look in more detail in light of recent trends, you look at why would this matter when we start looking at risk? Well, now we're dealing with COVID-19, and the testing is new, and accuracy is challenging. You've seen everything on the news. Some people said that, hey, these tests are 60% accurate. They couldn't get the test right. There's different chemicals. They didn't buy them from the WHO. Instead, they try to make their own, and testing has been a problem. I do think it's going to get much better, but when we talk about risk and rules to lessen the risk, you can apply it to things that affect your everyday life. As far as testing, things that need to be done to make sure we're getting the good tests. So PCR tests may produce false negatives, failing to identify evidence of the virus. Sometimes false negatives result from human error or problems with the procedure. Given the test too early or too late, for example, can lead to a false negative. The accuracy of similar tests from influenza is generally 50 to 70%. So here we want to test everybody so we can isolate them and contain them. It helps get businesses open. It helps seeing where the problems are. And we have tests that are only, on the neighborhood of 50 to 70% accurate. So when we start looking at things that impact us, we need to really go with these three rules. We can't skip any of them. And these three rules to lessen your measurement risk are: know the right requirements. First rule involves knowing what is needed to accomplish the task at hand. Choose the right equipment. Always choose measuring and test equipment that can achieve the measurement tolerance required. Have the right process. Last rule requires having a training program approved for training to validate the individuals performing the calibration or using the equipment. That's a big thing. You're throwing people in the wind and saying, hey, go do these tests, and they're you know they're flawed, and they're getting better. I don't want to say anything negative because it's a situation we're in, but these three rules are so important. Make sure people are trained, because you do not want a false negative. You do not want somebody that potentially has this virus to be out in the world spreading it. You're never going to want that. So if we talk about the rules in more detail, rule one is know the right requirements. The first rule involves knowing what is accomplished. So for us, the more accurate the system, the higher the cost will be to procure the equipment and have it calibrated. That's almost as true in any industry. You want something super, super accurate. So to get super, super accurate, the costs are going to go up. For most tests, a TUR of 4:1 will meet the guidelines set forth in ANSI Z540.1 of ensuring the total risk is less than 4%. That's true. If the requirement is 0.1% of applied and the stability of the device is 0.2% over a 1-year period, the device would need to have the calibration interval shortened. That one is simple. Lots of people do this. Hey, I have a device that I want the accuracy to be 0.1% of applied. Then it comes in for cal and it shows that it's been out, and it's out by more than 0.2% over the year. The customer says adjust it. We adjust it, and they go on using it as 0.1. That's not the case. Here's a case where you really want to look at stability. And A2LA has a interesting document here. When we look at, these are the minimums. They come out of R205, which is now going to be replaced. But A2LA has this nice, just really simple to use spreadsheet for calculating uncertainty. It's repeatability, resolution, reproducibility, reference standard, uncertainty, and here's the big one: reference standard stability. Lots of people forget about this stability. You should not forget it. I'm so happy that it's here. And that we can look at it, because that is a big factor. When we put in that 0.2, and we're not going to get a 0.1 down here, we're most likely going to be able to divide that by √3. Also, when we're looking at uncertainties and we're looking at things, if you want to lessen it, Morehouse, we have uncertainty sheets. This is available under Smart Tools. This one specifically is to do force measurement. You can look at it. You can look at the red tabs here. Lots of good stuff. here we still need to do a repeatability study, but we have stability, we have lots of things accounted for. Right here's reference standard stability change from previous. We do it per point. Lots of things, good things. Both companies, like I said, Morehouse, A2LA has this one. You can go to A2LA and get their just standard uncertainties to do that. But more things to look at, more tools to help you, all good. So what happens when rule number 1 is not followed? Here's the Texas BP refinery before and immediately after explosion. In a 335-page final report, federal investigators from the U.S. Chemistry conclude that organizational and safety deficiencies at all levels of the BP Corporation caused the March 23, 2005 explosion at BP refinery, the worst industrial accident in the United States since 1990. The report calls the U.S. Occupational Safety and Health Administration to increase inspection and enforcement of U.S. oil refineries and chemical plants and to require the organizations to evaluate the safety impact of mergers, reorganizations, downsizing, and budget cuts. So what happens here? Why does this blow up? Well, we have a distillation tower and attached blow drum. The drum overfilled, 7,600 gallons of flammable liquids released, and it's ignited by an idling diesel truck. So high-level alarm malfunctioned. Level transmitter was miscalibrated, outdated 1975 data sheet. Level transmitter indicated liquid level falling when it was actually rising. Although a high tower alarm did activate in the control room in early morning hours, the second high level malfunctioned. So people just didn't know what to do. It was a huge ordeal, huge problem when you have this. And you just think about it. I mean, what's going on today is bad, but ironically, if a person doesn't buy a bat in the wet market, they think that this whole COVID-19 started from a bat. If they cook it 1 degree higher temperature, if they cook it longer, maybe if China just bans the freaking sale of bats and shuts down the wet markets, none of this happens. So really problematic on things and knowing those, relating it back to the, COVID-19. But this one didn't need to happen. This is, if we keep looking at it, you start looking at root cause analysis, part of, ways you can go about diagnosing problems or, your events and the forms, cost cutting, production pressures and failure to invest, lack of preventative maintenance and safety training. And then we have the famous one, procedural workarounds to compensate for the deteriorating equipment. That should never happen. The cost, 15 deaths, 180 injured, over $2 billion, including lawsuits, the whole way through. I do want to say that this is example. Scott Mims does an excellent course on measurement risk. He has a 2-day course. I highly recommend anybody that's watching this seek Scott's course out and take it. So number 2, choose the right equipment. Always choose measuring and test equipment that can achieve the measurement tolerance required. If you need to certify that an instrument is within a tolerance of 1%, you cannot use a standard with a 1% tolerance to perform the calibration. That's a 1-to-1. It's going to be a lot less than 1-to-1 when you do everything. Several manufacturers do not understand TUR and do not include the instrument's resolution or repeatability or reference standard used to perform the calibration in their accuracy claims. Yep. Or they do understand TUR and they force it on the end user. They say, hey, we're not going to do it here. We're going to force it on the end user. One of these instruments, on some of these, no reference standard in the world may lower the risk if the instrument shows virus. So choose the right equipment. Always choose measuring and test equipment that is capable of achieving the measurement tolerance required. Again, this calibration, here's an example. It's calibration of a scale in our 804,000 press. The scale is repeatable within 10 pounds and has a resolution of 10 pounds. So in this situation, you have a resolution of 10 pounds and it's repeatable within 10 pounds. You're going to look at this scale, and in all cases, the best we can do is 12.1%, unless actions are taken to reduce repeatability or resolution. We start looking at it. Here I'm showing a standard deviation. Here's how we get repeatability. We make multiple measurements and we take the repeatability of those measurements. So right here, I take 4 measurements and my standard deviation is 5.77 pounds. So that's what I'm going to look at. And my resolution's 10 pounds. That's not going to change. That's what the device, you're going to have to buy or have the manufacturer, which they probably could cut the resolution down to 5 pounds or something that would make this a lot better. But if we break it down, you start looking at resolution, you look at repeatability, you look at TURs, you look at expanded uncertainties, and you can see that TUR, the CMC's not really doing much to the TUR until you get to, 0.1%. So this is clearly the issue here with anything is not the reference standard. The reference standard, as long as 0.5% or better, the TURs, it's the instrument that we're testing. So if we look at how we can fix it, we can raise the tolerance. If somebody wanted a 4-to-1 TUR, we would need to raise the tolerance to 0.52%, and we would have to have dead weight. We would have to use dead weight as a primary standard. So this would have minimal risk. Other thing we can improve if we just improved repeatability. We're not going to get to 4-to-1 TUR if we just improve repeatability, but we could take more measurements. And if we take more measurements and improve the repeatability here, right here, we can get to a 1.731. This is assuming dead weight. It's very hard to calibrate these scales in dead weight. So that's another thing that we're looking at. More than likely, someone's down here using a secondary standard at this 0.25, and they're having a TUR 1.58 to 1. This is what we did in a study. We took this scale, we sent it down to JAWS, Jackson Aircraft Weighing Services. They took the guts out of it. They made a lot of modifications to it, and they improved both things, resolution and repeatability. We have a paper on this. It's online that shows, and it's how we're derived our CMC uncertainty parameter, because we actually used the scale as a UUT with a resolution of 2 pounds. So with a 2-pound resolution and a CMC of around 0.22, a 4-to-1 can be achieved. This is important. A lot of people are trying to get this. A lot of people are mindset military still want the 4-to-1, and they're able with secondary standards to achieve about 0.2 to 0.3. So if they get everything together, it's really the scale. The whole thing in this is it's the device. You're just not going to be able to make that statement of conformance or compliance with this device if you have that resolution of 10 pounds and your repeatability is what it is. It's just very, very difficult using the current equipment that's out there. So what else can you do? You can take more readings, which takes you more time in the lab, but you can say, hey, repeatability, I can take 20 readings. Here we just started taking more and more readings, and we got the standard deviation down. So doing this, this graph here basically shows if I use dead weights, I can get my risk. If I use dead weights with this scale and I take more readings, I can get our risk down below 2% on each side, or below 4% total one-sided risk. But as soon as I break from dead weights and I'm breaking down here to 0.25, I can no longer get this in. Again, even if I take multiple measurements, that resolution is just killer. And it's why you have these different groups that are saying, hey, pass the risk to the consumer. Let's not put resolution in our denominator. We'll pass it to consumer where they can take care of it when they actually weigh the airplanes or whatever. Or you can take care of it on, which I'm a much bigger fan of taking care of it on the side as the calibration laboratory. And you can say, hey, look, we can calibrate this. This is what it is. This is your risk. You have this. Know that you have X% at 0.25. Know that you have a 6.43% chance of being out. So just something that, and this also assumes the location of the measurement is perfect. So it assumes 10,000 pounds is 10,000 pounds. If we're over here at, the resolution such that this thing's only going to read, 10,000 or 9,990 or 10,010. So, again, the only way to lower the total risk is to buy a scale with better repeatability and resolution, or change the method, lower the acceptance limits. Evaluating all components in a system is critical. Here we can look at some other ones. is an MSI Portaway, a very good instrument. Most of them, about 80%, come in and hold their cow. It's pretty amazing. But it's just an example where the location of the measurement is key. So the specification of the unit model is 0.1% of applied plus or minus one count. If we look at this when the measurement's perfect, measured value up here of 500. And then if we look at it down here when it's 501. So like I said, these instruments have very tight tolerance, but if and most of them come back in, the 20% that are typically out come out because of these first points where it's really tough. So here at 501, our total risk is 4.23%, which is too high. So this is a situation where we're going to have to adjust it, and the end user's then going to have to make the determination if it's too high, if that risk was too high or not. It's just one of those things that's reported. They're tough to get in. When they do go out, that 20% that do go out, you get them back in. It's fine. It's just the remainder of them just typically really good and hold their measurement. So like I said, if it shifts at all, it is tough to make the statement of compliance. You can look at this as, as a PCM. This is one of the a piece of equipment. Its primary purpose is to eliminate hand weights. A lot of people stack on these handheld force gauges and this. A lot of people stack weights, which ergonomically produces a big safety hazard. So this machine was created to allow a portable set to do, like handheld force gauges, digital force gauges, load cell to load cell. But when we start looking at it, UUT of 0.5% of full scale, 0.1%, and 0.25, we're just going to start looking at what's it take, to be in. So CMC of 0.2% and a UUT resolution of 0.2, as long as the UUT reads between 995.4 and 1000.4.6, the system would be enough. So that's a 0.5%. So we're looking for plus or minus, really plus or minus 5 pounds. But in this, we can't have, we have to subtract the uncertainty of the reference, and we have to look at the resolution and repeatability. So in this case scenario, we have a TUR of 21.65 using our PCM, and we still can't make that statement of compliance unless the measurement falls within this. And that's really what we're saying. So that's I'll have less than 2% risk if my measurement is above 995.4 and under 1004.6. So I have my car scenario. In this case scenario, I have a long, huge acceptance limit, and I can push it to the edge and still make a statement of compliance. 0.2%. So now we have a 0.1% force gauge. A lot of them are 0.1%. This is basically saying, okay, instead of 499.5 to 500.3, I'm going to subtract about 0.2 off of this. So I have, as long as it reads 499.7 to 500.3, you can see down here TUR dropped. I had a much higher TUR on the other one with acceptance limits. Now I have a TUR of 4.33. It's basically saying, hey, my graph here is a little bit wider and I have less room to be in. I'm probably in a normal parking space here where I do have to worry about the door beside me, but not as much. It's a little bit taken away. And then if I want to have something like almost a 1-to-1 TUR, if I want to calibrate another load cell and I want this load cell to be better than 0.25% of full scale, I can do it. I have a CMC of 0.2, and what I'm looking at here is 1999.91 and 2000.09. So I have very little room. If you look at this graph, I mean, I have to almost have a perfect measured value in here or just a perfect, which I'm in that car door scenario where I need to, shimmy out of my car door. I cannot open the door, so I really need to be careful and have my measured value. That location of the measurement needs to be perfect in this, almost perfect in this scenario, or I'm not going to be able to make that statement of compliance. So big difference from being able to swing the door open. I can go all over the curve and have lots of room to say something's in, to I have very little room in this scenario. All scenarios you can use the device. It's just as the accuracy gets requirements get greater, tolerance of 0.025% of full scale, you just need to be that much more critical on that location of the measurement to call the device intolerance. So, and then I wanted to say there's other methods. Well, this is using method 5, which the old ILAC G8 recommended. If we use method 6, which you can do, that's a method in ANSI Z540.3 handbook that gives us a little bit more room. So there are other methods available in this case. But the important thing is on the right equipment, it can raise or lower your TUR. Different equipment types have different, CMC uncertainties parameters, which can raise and lower the TUR. Different reference standards can make the repeatability UT better or worse. So if you have a reference standard the goal is to have a reference standard that's plumb, level, square, rigid, and has low torsion. That's the goal. Any of those things that just aren't in line are going to make it worse. Also, hydraulic versus dead weight. On dead weight, hydraulic, you're going to have creep. On dead weight, you're just going to have that load there, and you're going to have creep on the scale. But the stability of hydraulics would factor into the CMC uncertainty parameter. Different reference standards have different resolutions. If we're using dead weight, applying masses, adjusted for gravity and air density and material density. If we're applying the right masses, then we're going to have 0 versus a load cell, which could have a resolution of 0.15. And changing the reference standard type will change the process, which will result in an increase or decrease of the CMC uncertainty parameter. So rule 3, have the right processes. The last rule requires having training program and proof of training records to validate the individuals performing the calibration or using the equipment. Important, maintain and follow procedures that adequately support the end performance. There should be a process in place that ensures all aspects of standards are being carefully satisfied in the calibration process, and use of proper adapters and making sure the instrument's calibration matches how it is being used in the field in the lab. This picture, sad. Apparently lower margins of safety existent. This is cranes. Several crane experts, after closely examined photos and videos of the crash, said they believe pins were removed early. Hey, they didn't follow the process. And they say it's a practice that has become common in industry, a way to save time during disassembly, despite the safety risks that they say it brings. Look, this happened. This was Seattle. Then we had other ones across the country. High winds and removing safety pins kill people. It's just foolish. Another example here I have of Cox Brain Lab. Basically, February 24th, 2010, Cox announces Brain Lab stereo tactic radiation therapy received an increase in radiation dosages. So they overdosed 152 cancer patients, 76 of which received up to 70% higher than prescribed dosages. Radiation system used to treat areas of 1.1 centimeters. So basically, a Cox Health chief physicist incorrectly calibrates this in 2004. It goes undetected for 5 years. People were overdosed when they shouldn't have been. And then in 2009, guess what? Someone receives the training they need, and then they find out that they've had 5 years of this. So although the calibration error was corrected as of February 2012, lawsuits are still going on. Just bad. There's a huge write-up of this. I have all the evidence. This is another one that Scott had given me, so thank you to Scott Mims for that. And then we have this. We have advertisers clearly showing things like, hey, the good way to measure torque. Well, it's not. So you have to be careful. You hear words like, fake and, a lot thrown around today, but there are advertisements that are out there that are wrong. And this is one of them that's just, it's not a good way to measure torque. There's this picture. If you look at this picture and we do the formula, torque is lift force times the sine, and we assume about 45 degrees based on that angle. Just follow the equation. So basically, looking at this picture, we're guessing there's a 29% error. If you use this to measure torque, your measurements are going to be out at least 29%. If they reshot this picture and they did this at an angle of 90 degrees, right? We would have a lot more problems figuring out the errors. First off, it's probably not going to be 90. Second, it's the length. How good is the length measurement? And if we just look at it in more detail, but that's not what they did. They deliberately took this piece where the angle is off by maybe 45 degrees, maybe it's 40. That error is almost 30. I can almost guarantee anybody that this error is almost 30 degrees, and it's a shame because it's not good practice. It's not a good way to go. This is still up. It's a manufacturer. It's still up on their website, and they need to correct it. They need to correct it to 90 degrees because if people are out there making these measurements, they could put our lives at risk from faulty measurements. Example of not following the right standards. Here's a E74 Cal. We see this all the time. It's basically saying the Class A lower limit right here is 192.3 pounds. It's not true because the first force point is 500. You're not allowed to take non-zero force point. So 8.6 says the verified range of forces shall not include forces outside the range of forces applied during calibration. If we continue to look at this, it's not true. Some calibration providers claim 0 can be used as a first calibrated test point. Not true at all. 7.2.1 of the standard says in no case should the smallest force applied be below the lower limit of the instrument as defined by the values 400 times the resolution and 2000 for class AA. So we have a full webinar on ASTM. This is just sloppy. If you have a report like this, you cannot use this device below 500 pounds. People use, and they are not in compliance. So if you're using a device with 0 as a first point and you're using it between the 0 and the next, non-zero force point, you're wrong. Stop doing it immediately. It's not right. Auditors are aware of it. They should be writing you up. It's not per the standard. The providers claim things that just are not true. The right calibration provider has measurement process and certainty capable of meeting your needs and follows published standards. They will also help you. They will educate you on what matters, because if we take a lot of money, it takes a lot of money. Calibration, I've not seen calibrations be cheap anywhere. So it's a lot of capital, and you want to make sure that the money that you spend is getting you the results that you need. So education is key. Educating customers on what matters is key. It's what we're passionate about. We're passionate about making the world a safer place. So we're going to do these things. We're going to replicate how the instrument is being used. We're going to ask those questions and do everything we can to do that. We're going to use the right adapters to ensure results are repeatable. We're going to have discussions on adapters. We have technical papers on adapters. The one won an award at NCSLI. It was one of the best papers. It did not win best overall, but it won best in the group. Has competent, again, the calibration provider is going to have competent technicians with training records. Very important. If you have somebody that you want to do something, you're going to want make critical measurements. You're going to want them to have some training, especially if you're sending out a test that let's go away with instruments. If you think you have COVID-19 or coronavirus, if you think you have COVID-19, you're going to want that lab to do the best they can, because you're going to want to know if you have it or not. We've had numerous friends come back with inconclusive results, which puts you in what is it? Imagine your load cell, inconclusive. It may be good, it may not be good. It's inconclusive. So that's not going to happen with load cells. We're going to tell you, and we're going to tell you the risk. You want the person used for cal provider to follow published standards. You want them to report measurement uncertainty correctly, and you want them to be, rated highly and reliable for on-time delivery. So it's, so if we're looking at a load cell system and measurement risk, you want to choose the right load cell system for your application. And same with scales. Maybe the scales may not have the resolution you need. An example, an S-beam load cell is not going to perform well for ASTM E4 calibrations and compression. That's from our adapters. If you side load the one that we show, if you side load it just a little bit, it's got a 0.745% error, or 0.752% error. So know the manufacturer considered when they set the unit specifications. I've heard of truck scales where they said, they show the average. They have a truck drive by 3 times, they do 3 measurements, and then they report the average. Now in practice, you're not going to have a truck, hey, go circle around. You're not going to take the standard deviation of 3 measurements when you're measuring a truck to see if it's safe for the weight's safe for the roads. It's just not going to be done. So you have to really dig into what the manufacturers are doing. Are they applying good metrology principles? Several are not. So, it's a buyer beware scenario. Choosing a readout that is stable with enough resolution is going to yield the best results. We showed it with that truck scale example. And none of this matters if your calibration provider cannot calibrate to the accuracy required, or if they do not follow published standards. So yeah, if you have an accuracy requirement of 0.5%, using a lab that's 0.037 is probably not going to work. Using a lab that's 0.25, maybe. If your accuracy requirement is 0.2, 0.2% of full scale, you shouldn't use any lab that has a CMC uncertainty parameter of higher than 0.2. You should really be looking for dead weights at that case. So if you really want to lower your measurement risk, you're going to have the calibration provider replicate how the device is being used. You're going to have competent technicians, which is a requirement for ISO IEC 1702527 section 623. You're going to use the right equipment, which is a requirement for section 6.45, and you can lower your uncertainties through your calibration provider, again showing this graph. And our mission is to be regarded as the best independent force and torque calibration resource in the world by providing realistic solutions and continuing to develop new products to meet customer needs. We also like to defy the average and meet 100% of quality delivery and overall customer satisfaction. We fill out event forms. We do everything possible for the standard. If we don't get anything right, we work with you. Lots of people say it's not. You really don't realize the company that you're with until you have a problem, and then when you have a problem, that shows on how a company is willing to work with you. We will work with you. We will work with everybody in this time of need. It's 2020. We're going through things. Call us. Talk to us. If you have questions, concerns, if you have, if we can help with uncertainties, if we can help with anything, we have, video guides like this. Anything we can do to help you make better measurements, we want to do. That drives us. It is our passion. We want you to use us for calibration, of course. Don't want to say we don't, because we really feel that we can help you. We can make you better. And by making you better, you will do better for your customers, and hence you will make the world a safer place. And to leave that with something that I really like, Grace Hopper, a fantastic metrologist, says one accurate measurement is worth 1,000 expert opinions, and that's really what it is. We have opinions circulating everywhere on everything, misinformation going everywhere. So let's cut the BS. Let's rely on science. Let's get our measurements good. Let's start making better measurements today. And I implore you to start using or thinking about, contacting Morehouse if you have any questions or if we can help you, because we will help you. We will make you better. Thank you for your time. It is valuable. Thank you for watching this. Info@mhforce.com if there are any questions. Thanks.